So the first topic which I want to talk about today will be subject which I was hoping actually to discuss yesterday. What will happen if we confine charged particles into a wire of a conductor, and when the current flows in that wire, then there will be a force exerted by the surrounding magnetic field on this wire. More precisely, it is force exerted by the source of the magnetic field, but we can think is that the source produces field, and then the field interacts with the wire. Now, the reason that the force is exerted on the wire is because the charge carriers, when they flow in the wire, they are confined to it. They cannot jump out from the wire. If there is a force which is trying to pull them out from the wire, they will pull the entire wire with them. All right. So let's say that we have wire which is placed in magnetic field, and there is a current flowing in this wire. And I'll derive now an expression for a force exerted on a tiny piece of the wire. So let's say that I will take a piece of a differential length. Cross-sectional area obviously is not the differential, it is cross-sectional area of the wire. So although it looks over here that the segment is longer than wide, in principle it is supposed to be a narrow slice of that wire. And I marked here the magnetic force exerted on this segment. Now, how this force is exerted? It is that, let's say that it is copper wire, so it means that there are electrons flowing in that wire. They will be actually flowing in the opposite direction than the current, but we can even think that we have a wire made from something in which that positively charged particles carry the charge through that wire. So in the derivation of the formula, I will consider positively charged particles carrying current through this segment. And well, all of those charged carriers which are in this volume will experience the magnetic force. They will be pushed by the magnetic field in this particular direction, and we can recognize why is it in this direction. So let's think that we have positively charged particles traveling through this segment. So velocity of the particles is consistently with this drawing, we will have velocity in this direction. Magnetic field is up. So now the thumb shows that the magnetic force will be to the right on all charge carriers which are traveling through this segment. All right, let's now evaluate the force exerted on the charged particles in the segment. And now, because they are confined to this segment, so rather than bending their paths, it is that they exert a force on that segment, because the segment, the material of the segment, the lattice actually holds them, right? Which means that the lattice exerts a force which balances the magnetic force, right? Now, according to Newton's second law, if the lattice exerts a force which balances magnetic force, it means that the charge carriers exert a force on the lattice equal to the magnetic force. All right. So let's start with imagine a single charge carrier traveling over there, and write an expression for the magnetic force. So it will be charge of the charge carrier multiplied by drift velocity of the carriers. And I wrote drift velocity as a product of magnitude of a drift velocity and a unit vector in the direction of the current in that segment. I use symbol S for it. So vector S is in the direction of the current, which is the direction of the orientation of the segment. Can you see it? Multiplied by magnetic field at the location of the segment. So this expression gives me a force on a single charge carrier now the force is on the segment, so I have to multiply it by the number of charge carriers in the segment. Well, that quantity depends on the volume of that piece. So I wrote it that it's cross-sectional area of the wire multiplied by the length of this wire multiplied by the concentration of charge carrier. Let me remind you that concentration is a number which says how many charge carriers we have per unit volume. In other words, here I have number of particles per unit volume multiplied by volume. So this gives me number of particles in this differential fragment of the wire. Now I will combine quantities because I can recognize, for example, that this is a unit vector in the direction of the segment. ds is a length of that segment. So if I combine these two quantities together, I can write it down that way. Now, do you remember what I called this vector? Well, I gave a name to this vector, and I want you to call it that way. I called it the segment vector. And let me remind you again how I defined that segment vector. Segment vector is defined in such a way that its orientation is the same as the orientation of the segment, and the magnitude of the segment vector is equal to the length of the segment. Why don't you repeat this definition to your neighbor? How segment vector is defined? Go ahead. Mike and Jerry, why don't you? Can you sit down a little bit? Mike, can you sit down next to him? I mean, over there. Oh, he gets closer. Okay. Right. Mm-hmm. Correct. Mike, can you tell him that? Yes, a segment vector is defined in such a way that the orientation is
segment vector
is the same as the orientation of the
magnetic field vector.
No, segment.
No, segment.
Yeah, orientation of a segment vector is the same as orientation of the segment. So how about that? Let's say that I had this is the segment. What would be the orientation of the segment vector? Same, this way, right? If I somewhere have a segment like this, orientation of segment vector is like this. Now, if this is the segment vector, what's the magnitude of this vector? It's equal to the length. Now, the most common error which people do is to confuse segment with segment vector. That the people identify that it's the same thing. All right. And now I combined all those scalar quantities together. And well, there was a reason that I combined them together, because I can recognize that this expression really represents the current flowing through in the wire. Now think about it, because imagine a cross-sectional surface here. How much charge is transferred through that surface? Well, it is related to how fast the particles move, right? So now this VD, it says which particles will actually cross the surface. So all particles whose distance is smaller than v magnitude of drift velocity times 1 second will cross the surface in 1 second. Yeah, let's repeat the same analysis as we did sometimes. Imagine that we all start moving forward. Let's say 8 meters per second. So let's see, 8 meters is about 8 relatively long steps. So it will be 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is 8 meters. Up to this point is 8 meters. Let's say now that we all move forward with speed 8 meters per second. And let's say that we have capability of crossing the front wall. Who will cross the wall? Raise your hand. Teja, how about you? You think that you would cross? Or you said that you don't think so? Shout it. I didn't hear you.
No, not 1 second.
You will not cross it in 1 second. Why not? Because you are going 8 meters per second and you are at least 10 meters away from the wall, right? So that's right. Everybody who is just 8 meters away will cross that front wall. All right. Now, the charged particles in this wire move with speed v sub d, magnitude of drift velocity. So from how far the charged particles will be able to cross this cross-sectional surface? Well, from the distance, magnitude of drift velocity multiplied by 1 second, right? So let's say that that is up to that point. All these particles will be able to pass in 1 second. All right. Now, if I multiply it by cross-sectional area, so if I multiply this magnitude of drift velocity multiplied by 1 second and multiply by cross-sectional area, it gives me the volume in front of that surface from which charged particles will be able to cross the surface in 1 second. Now, n says how many of those charged particles is per unit volume. So if I multiply this n by that volume which I just evaluated, it will be the number of particles which will cross the surface in 1 second. And if I multiply it by charge of those charged particles which are traveling, I will get the charge which is transferred through that surface in 1 second. Do you see that? Now, charge transferred through a surface in 1 second represents what? Current, correct. This is why I wrote it. So this entire product here gives me current flowing in this wire. Well, this is product of IDS. So in conclusion, we derived here a very important formula for the force which is exerted on a differential piece of wire in magnetic field. All right. Now let's use this formula to find out force. Let's say that I have a piece of wire, which is why don't we think about actually that this wire is in the plane of the whiteboard. And how about if I mark if this wire is in magnetic field, uniform magnetic field like this. Oscar, what is the direction of magnetic field? It's coming out from the whiteboard. Let's say that I make current. I push current through this wire. How about if I start actually with simpler case? Let's have a straight wire. piece of straight wire of length L. And let's now find out what is the value of the force exerted on this entire piece. Because on the screen, the formula on the screen gives me what force. Let's actually go through the symbols. What is the F in English? Is the differential force exerted on the tiny fragment, on the differential fragment of the wire. What's I? What current? It is current, but which current? Current flowing through that fragment. Now the next symbol is difficult. What is it? The segment vector, correct? And B is the magnetic field vector at the location of that segment. Now, Adam, would you be willing actually to explain what is segment vector?
The segment vector is oriented the same direction as the segment, and the magnitude of the segment vector is the length of the segment.
Correct. Good. Yeah. So I think that we comprehended it. Well, how properly we comprehended it, we will see when we will try to figure out the force exerted on this wire. Actually, I make this more clear that it's a piece of wire, so I make it as a rod. All right. So in order to find out force exerted on this entire rod, I will have to divide the wire into pieces, right? Now, so for this piece, vector ds would be to the right. If I multiply, yeah, okay, so this is vector ds. It's relatively short. I mean, it's has differential magnitude. This vector has differential magnitude, obviously. So the force exerted on that, magnetic force exerted on this differential piece is equal to the current flowing in the piece times segment vector multiplied by magnetic field vector. And if I want to find the resultant force on this entire piece, what do I have to do? Integrate over this wire. So I have to integrate this entire expression over the wire. Now, whatever is constant in the integral, now constant in the integral means independent of the variable of integration. Now, what do we use here as the variable of integration? These differential vectors, right? So whatever is independent on the piece can be pulled out because it will have the same value. So can I pull out current in front of the integral? Yes, because if I think about other pieces, current through each piece has the same value. So I can pull out I in front of the piece, of the integral. Well, this is, how about the S? No, because it is related to each piece. How about B? And actually, I'm happy that you are thinking, because it's not obvious. It depends really on this, where do I put it? In general, it is a function of the piece. At each piece, we can have different magnetic field. However, I started the introduction with saying that that piece is in a uniform magnetic field, which means that magnetic field vector at each point of the magnetic field has the same value. So I can pull it out in front, outside of the integral as well. However, remember that vector product is not commutative, which means that I cannot pull it out in front because it's on the other side. So I can write it down that this is integral along the wire of those vectors ds and pull out this factor on the other side. All right. Now we have here a relatively simple integral. We have to add all segment vectors. In other words, I have to add this vector, 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 and so on. All of them. And I bet that you will guess a wrong answer. If I add all those vectors together, what am I going to get? Answer. What is L in English? Say it in English. The what? The length of the entire wire. And this is what I thought that you will answer. Length is a vector or a number? Number, right? Now, if I'm going to add tiny vectors, what am I supposed to get? A what? A vector. Yeah. So obviously, when I add all those pieces, I won't get the length of the wire. What am I going to get? I'm going to get a vector. What vector? Let's do it slowly. So if I add the first two vectors, what am I going to get? I'm going to get a vector, right? Now, describe this vector. Where is the tail of the sum and where is the end of the sum? Well, tail is here, head is here. But if I add the first two vectors, I will get a vector like, oh. I'll get a vector like this. Now, if to the 2 I add the next one, what am I going to get? How long? From here to here. Now, if I add another one, it will be from here to here, right? So if I add all of them, I will get a vector whose length is equal to the length of the wire, but that vector is going to be oriented along the wire. Do you see that? All right. So I can write down that it is current flowing in the wire multiplied by this, by vector L times magnetic field vector. Now we have to recognize that that this vector is a vector from one end to the other end of the wire. I think that Sam has a question. Can you really shout? What's your question?
What if the wire turned? Like then wouldn't?
When wires bend, right?
Yeah.
This is what I actually originally wanted to ask you. I figured out that first we solve simpler problem, and now we are going to talk about what will happen if I bend this wire. Indeed. So how about if this time I'll take a wire of such a shape. Well, let's see what will be different in the calculation over here. Well, I have to again to divide the entire wire into pieces. For each piece, I will mark a segment vector, and so on. let's say that I'm considering this piece. Well, up to this, I mean, this is true no matter what, right? We never use here any. I mean, this up to this point, it's generally a general calculation. So, magnetic force exerted on the entire wire is equal to the sum of magnetic forces exerted on the pieces. Now, the magnetic force exerted on the piece depends on the current flowing through the piece, segment vector assigned to the piece, and magnetic field. So there is nothing. I did not. So it doesn't matter now if the wire was bent or not. Well, let's see now at the next step. Is the next step possible for this type of a wire? So can I pull out the current in front of the integral? Who votes? Who thinks that it's possible? Who thinks that it's wrong? Well, those of you who thought that it's correct, you were right. Current through each piece is the same. Recognize that the pieces really are connected in series over here. Now, if it is in a uniform magnetic field, can I pull out that magnetic field vector? Who believes yes? Who believes no? Those of you who believed yes, you were right. At every piece, we have the same value of magnetic field vector. So actually, this step was possible as well, which means that this calculation is correct so far. And now let's try to integrate that. What will happen if we add all segment vectors? And Sam, can you see that? What will happen if we add them?
It would just be like the displacement of.
I understand the displacement, but nothing is really displaced here, so it isn't formally displacement. I think Taya has would be able to rephrase it, because I think that she understood you too. Did you?
It's gonna be like, it'll be if you're a straight wire of the same length, but sort of like.
That you make a straight wire of the same length?
Yeah.
Then you didn't. You didn't comprehend Sam, because I don't think that Sam meant that. Did you? No, I know that you didn't. Yeah. Okay, Robert?
Would be the starting point of the wire from straight to the beginning of the wire?
Robert interprets your answer that it's a vector like that. This is what you meant, right? Correct. I recognize that this is what Sam really meant. Yeah, because, well, think what will happen if we add these two, right? We will get a vector from here to here. The next one from here to here. It will be always from the tail of the first arrow to the head of the last one. So, for example, if I add up to that point, I will get an arrow from here to here. If I continue adding, if I add to that point, I will have an arrow from here to here, right? So in the result, I'm going to have an arrow from the beginning of the wire to the end of the wire. All right. So why don't I mark it actually as vector L? And so here, instead of small l, I will have capital L. And I changed it from small l to capital L for this particular reason. I will ask you now to compare these two integrals. I mean, what am I going to get? What am I going to get? What will be the result of these two integrals? Now, in order to do it, you have to tell yourself in English, what are we doing? Yeah, so here, what are we adding here? And what are we adding here? Well, we were just adding, we were just calculating this integral, 3 minutes ago. What were we adding here? Which vectors? Correct. Vectors. Which vectors? Segment vectors, right? So when we added segment vectors, what are we getting? A vector. What vector? From the end, from one end to the other end, right? An arrow from one end to the other end. And so I will call it L. What am I going to get here? First, we have to realize what are we adding. What is the S? No, it's not segment. Actually, if we add all those segments, what are we going to get? I mean, I don't know if we, I'm not precisely sure how we, what we understand by adding segments, but let's say that we rearrange the segments. What are we going to get? Yeah, we add the segments, meaning that we stick one segment to the other segment. What are we going to get? We won't get the length of the wire. All right. Let's say that I will collect here the segments. Yeah, I got six segments, and now I'm going to add them. What did I get? Six erasable markers. Well, I mean, what do you see here? I mean, six erasable markers. Well, it's a rod, right? It's an object. If I assemble those segments, I get an object. So if I assemble, what will happen if I assemble all pieces of the wire? We say, I will get the wire. Right, so if I add the segments, I will get the wire. We are not adding segments here. What are we adding here? Segment vectors. We are not adding segments here. What are we adding here? Lengths of those segments. Correct. So if I add lengths of all segments constituting the wire, what am I going to get? Length of the wire. Correct. So then I will get length of the wire. Now let me ask you a question. One more question. Is this equal to magnitude of this? No. Right? And for this reason I wanted to use a different L. Yeah, because magnitude of this, what will be magnitude of this vector L? It won't be the length of the from head to tail. Distance between what and what? From one end of the wire to the other end of the wire. Right. How about if we think about this puzzle now? I will have a ring. What will be the magnetic force exerted on that ring? And I mean, you could do it from the very beginning, but we could recognize that for an arbitrarily shaped wire, we got an expression that magnetic force is equal to current flowing through the wire multiplied by vector from one end to the other end multiplied by magnetic field vector. From this, it's easy to see from this formula. Yes, Robert? 0. Magnetic force exerted on the ring is going to be 0. How did you figure it out that it's 0?
Well, because if you go from, choose any point.
Yeah, I choose, for example, this point as the end. The beginning of the wire. And indeed, end happens at the same point. So this vector L is a 0 vector for a ring. All right, now I have some experiments over here, an experiment over here. I have here a power supply. Positive terminal is here. So current flows this way, and back to the negative terminal of the power supply. Well, current doesn't flow because I control current now with this potentiometer. And I'll turn on potentiometer. And did you see that this wire was deflected? Which way it was deflected? This way, right? Okay. I want you now to figure out what is how about if I actually take it that way? And do the same experiment. Can you see how it is deflected now? I'm really pushing quite a lot of current through it. This time it is not deflected at all. It was deflected when I had such an orientation. Now it got deflected. I want you now to have a conversation and figure out what is the direction of magnetic field produced by this magnet. Go ahead and talk to each other. And actually you can, well, we can think about this formula here now. You don't have to think about differential fragment. Now instead of differential fragment, you can think about a vector from one end to the other end. From the end at which current enters the wire to the end where current exits the wire. So over here on which end current enters. Now this is the conventional current, so think about, well, the direction of the conventional current. And conventional current, I mean, a piece of wire behaves like piece of wire is a resistor, right? So current flows from higher potential to lower potential. In the battery, it flows from lower potential to higher potential usually. All right, so current flows, this is higher potential, so current in this loop flows like that. Which means in this wire, current flows in this direction. What's the direction of vector L, therefore? This way, right? Okay, so we have that current flows this way. We figured out that the force is exerted this way. What should be the direction of magnetic field to get it? Straight up, correct? Magnetic field is straight up. Just to make sure that it works, how about if I flip it? Let's see what will happen if I flip it. What do you predict if I flip that magnetic field? The deflection should be in the opposite direction. Oh, wow! We predicted the future. See that? I mean, this is the purpose of science. Then we can predict what will happen if we change something. We control nature now. Can I change something else maybe? Have suggestions? Ah, I know what I can change. What will happen now? We are predicting that the wire should be deflected this way. Ah, Alan, aren't we good? Great. I think that with this optimistic, optimistic thought, we can that we control nature. We can finish the lecture, today's lecture. So, oh, hold on. Yes. Aha, yes. Why it didn't work this way? Because, well, let's figure it out. So we had current flowing in this direction. Yes, Robert has. Let me give you the microphone and use the right-hand rule. Is it okay that we record you?
Yeah.
Yeah. All right. So show your hands.
Wow. Jeez.
Yeah. So current was flowing.
Oh, now I'm videotaped. Okay. Well, the current was down. I don't remember how the.
Yeah, current was flowing this way.
Well, current was flowing this way on the wire.
Right. Current was.
And the magnetic
Field was horizontal this way.
was horizontal this way, but when we switched it.
No. I mean, it was before we
What are you
switched.
talking about before?
No, when the magnetic field is horizontal, yeah, because now why we didn't see deflection when we turned actually from this experiment we were able to conclude that magnetic field is indeed along those screws in that magnet, because now our prediction is Robert's prediction is consistent with assignment of that magnetic field, yeah, because now current is flowing this way, right? Magnetic field is which way? That way, horizontal, right? So figure out the force.
Well, see, when it was standing up. Like
No,
this,
no.
It was pointed horizontally. So if you flip the axis, shouldn't it be pointing vertically?
Hold on. Over here,
Magnetic
in this
field
configuration,
The magnetic field vector was pointing this way when he had it set up like that. But when he switches it,
all right. Yeah, so over here, we figured out that magnetic field is which way? Up, right? Because current is flowing this way, magnetic field is up, force is to the right. Now, I make it this way. So consistently with the previous experiment, magnetic field now is horizontal, right? If it was up a moment ago, now it's this way,
Okay,
right?
yeah.
And now I'm turning current and I don't see any effect.
because you're trying to move the wire up and down.
Yes, because now magnetic field is, current is in this direction, magnetic field is this direction, so magnetic force is down. Yeah, magnetic force is down. So why don't we see the effect?
Because the wire can't move
Because
up or
the
down.
tension force increases here and balances that magnetic force. In that other configuration, well, gravity was balancing the magnetic force, but in order for gravity to exert appropriate, force which could balance it, it had to be deflected. Is it clear? Great, yeah. Thank you for the question.
Let's go to you guys.